Algebraic extensions satisfy a similar property to that of finite extensions. If you have a tower of algebraic extensions, then it is algebraic if and only if each floor of this tower is algebraic. So let me prove theorem 3. Well, again, let L be an extension of K and M an extension of L. Then M is algebraic over K if and only if M is algebraic over L and L is algebraic over K. So one direction, let alpha be in M. Of course, if it satisfies a polynomial relation with coefficients from K, if P of alpha is 0 for some P in K of X, then also this P is an L of X. So alpha is algebraic over L. And if now alpha is an L and we want to prove that it's algebraic over K, then it's even easier. Then also alpha is an M, and so alpha is algebraic over K. So L is algebraic over K. Another direction. So I have L, which is algebraic over K, and M, algebraic over L. I must prove that M is algebraic over K. So take alpha in M and consider the minimal polynomial of alpha over L. Its coefficients are elements of L, so they are algebraic over K. By the previous theorem, they generate an extension E, which is finite over K. Now, E of alpha is also finite over K. E of alpha is also finite over K. Since E of alpha is finite over E, alpha is algebraic over E, and this means that alpha is algebraic over K. Because since E of alpha is finite over K, then there will be some linear dependence between the powers of alpha. There is a relation between powers of alpha. Okay, let me give you an example. So consider the extension obtained from Q by adjoining, let's say, the cubic root of 2 and the square root of 3. This is clearly algebraic and finite over Q. And what is its degree? The degree of this extension is 6. Indeed, we have Q inside Q over the cubic root of 2 inside Q of the cubic root of 2 and square root of 3. The minimal polynomial of the cubic root of 2 over Q is x cubed minus 2. This is an irreducible polynomial over Q, which has this cubic root of 2 as a root. And so Q, cubic root of 2, is generated over Q by linearly independent elements 1 cubic root of 2 and cubic root of 2 squared. So the degree of Q with cubic root of 2 adjoint over Q is equal to 3. Now, the square root of 3 does not belong to Q with cubic root of 2 adjoint. Well, maybe the easiest way to see it is as follows, because otherwise one would have Q embedded in this cubic root, Q of square root of 3 embedded in this Q with the cubic root of 2 adjoint, and the degree of this extension is clearly 2, and the degree of this extension is 3. Well, 2, the degree of Q square root of 3 over Q would divide 3, which is Q of cubic root of 2 degree over Q. We have seen that the degrees multiply in towers of finite extensions. So this is impossible. Therefore, x squared minus 3 is irreducible over our extension and is a minimal polynomial of cubic root of 3 over this extension. And the degree of our big extension over Q cubic root of 2 is equal to 2. Therefore, the degree of Q cubic root of 2 square root of 3 over Q is 2 by 3 is 6. Well, I should have said this earlier. This fact is completely general, that the degree of an extension generated by an algebraic element alpha over K is equal to the degree of the minimal polynomial of alpha. So in general, proposition, the degree of k of alpha over k is the degree of the minimal polynomial of alpha over k if alpha is algebraic. I should have said this earlier. The proof is obvious since we have already remarked several times that k of alpha is generated by 1 alpha and so on alpha g minus 1 if this is d, and in fact this is a basis, independent. Well, in any case, this is a good practical tool to compute the degree of a finite extension. And I would like to finish with a little remark which might be helpful to understand the next lecture. So, a proposition. Well, let K in L be a field extension. So consider L prime, which is a subset of L formed by all elements algebraic over K. Then L prime is a subfield of L. One calls it the algebraic closure of K in L. Well, the proof is of course easy. If alpha and beta are algebraic over K, we have to prove that alpha plus beta and alpha beta are algebraic. But this is trivial by theorem, I guess, 2. Follows from theorem 2, since alpha plus beta and alpha beta belong to K alpha beta, which is a finite by theorem 2 extension of K.